There's homework due today. I think everyone has turned something in, and most of you, it's working great. So that's good. In fact, nearly all of you, I think, have done really well on this. The homework was to find main. Talked about how to do that, one possible way to do that. And there was some hints. And let me go through one possible solution to this problem. Just a solution. Your solution will probably be different. There was some that was shorter than this. There was some that was longer than this. There was one that I thought was just a really cool solution to this. But let's go through what I threw together a short file to do this. Let's just go through that real quick. Preamble is the usual start Python 3. There's a doc string and some imports. The only thing that might look unusual in here is this little thing over here, these little comments over on the side. These are hints to the Python MyPy type checker that it should ignore uses of these things because it doesn't have type information for them. Doesn't matter if you're not using MyPy, you don't care. So let's move on. So here's my main function. And this is the first piece of it. All it does, it's a doc string, but all it does is check the command line arguments and then open the file. And so I open argument 1, read binary. I then try to parse it as an ELF file, and I catch a bunch of different errors, like ELF error, which will tell me if it failed to parse it as an ELF file. And you'll see I've got some debug statements in here. They look exactly like print statements, with the exception that they have the word debug in front of them. It's the only difference. That way I can have them when debugging is on, and then I can not have to worry about that later. And it's good to build, if you're going to build debugging statements into your code, you probably should leave them in your code and then just have some simple way to turn them on and off. So anyway, after that, we have the text section, and that's pretty straightforward. I go get the entry point out of the ELF header. I get the text section by name. If I don't get a text section, then I complain with an error message, and I return 1 saying there was an error. Otherwise, I get the address of the start of the section. I get that from the section header, and then I will get the data that's present in that section. This is just an array of bytes. The array of bytes starts at, of course, index 0, but index 0 corresponds to this virtual address of ADDR. So I know ADDR corresponds to location 0. So ADDR plus 1 corresponds to location 1 in the array, and so on. And that'll be important a little bit later. So the entry point, I just do some debugging statements here. Entry point is here. Address of start of text is here. Length of text is here. So then I verify that the entry point is actually in the text section. That's kind of important. So I check to see if the entry point is less than the start of the text section. And if it is, that's bad. Or if the entry point is greater than or equal to the length of data plus the address of the start, right? Because this quantity would be 1 past the end of the bytes that make up the section. And so if that's true, that's bad. Either case, I say the entry point's not in the text section, return 1. Now I've got to get the basic block for the entry point. So here's how I do that. Create a disassembly generator for 64-bit x86. I set detail to true, so I get all the nasty, gory details. And then I create a little disassembly generator right here. And here's where that notion of the offset comes in and becomes important. I don't think anyone was fooled by this. This is basic computer science. This is like CS maybe 102 level stuff. So I know the entry point's address. I know the address of byte 0 of my array. So if I want to know the address of entry in my array, I just subtract those. And here I just do an array slice. right? I talked about array slices before. I just grabbed, here's the first index, colon, and then nothing after it takes me to the end of the array. Array slices are super cheap to construct. They're just done internally with pointers, so it doesn't copy the array. It just gives me a pointer into the array, which is actually what I want. The disassembly generator still needs to, all this is just still an array of bytes. There's nothing special about it. It does not know what the address of index 0 of this sliced array is. So I tell it the address of byte 0 is entry. And so now it has enough information, and it gives me back a disassembly generator. I create an empty array to hold my block, and then I just build the block. So for instruction in this, I append the instruction to the end of the block. I get the mnemonic, and I use that trick I mentioned in email to get it. If you didn't do that, that's fine. I didn't give you any that would trip you up, but some of them have prefix bytes, and that will ignore the prefix bytes. I took that in MNE. What I did not do here is worry about suffixes, and there are a few that make their way through some disassemblers. Move ABS is an example of one. Didn't worry about that. Not gonna worry about it now. It's fine. So here we go. And then I check to see if it starts with J. So that would be a jump or a JZ or a JE or any conditional branch. And there's some logic within the Capstone library you could use for this. I was lazy and just did this. Or if MNE was in the one of the list of things that will terminate the basic block. And that would be return from instruction, or sorry, return from interrupt, halt, and loop. If I found any of these things, that ends the basic block and I break out of the loop. If I run off the end of the text section, I just end this. So either way, I end the block when I find the appropriate ending thing or when I run out of instructions. So there we go. So then I print out the basic block. And so I check to see if I'm debugging. If debugging is enabled, then I just run through the instructions in the block and print them out so I can see what's actually in the basic block. So this is kind of handy. I could have just had the loop without this if in front of it, since all the things inside of the debug instructions, the loop would have done nothing if debugging weren't enabled, but I would have still had this iteration. And so this just prevents it from being even the initial iteration. So now, done that, I got the basic block. Let's check to see if it is long enough. And so I require there to be at least 3 things in it. Makes sense, right? I've got a set RDI, I've got to call something, and I've got a halt. So there have to be at least 3 things. And I want that because I'm going to reference stuff in the block. And if my array is, let's say, length 0, I'll get an out of bounds exception. And I don't want that. So, so I check for that. If it's too small, then I give up. I can't locate main. And I also put out a debugging information to say why I couldn't locate main, because that's kind of helpful. I check to see if the block ends with a halt. So I go to block, I pop the last thing off, I get the mnemonic and I look at the end of it. And if it's halt, if it's not halt, then doesn't match my pattern and I give up. Then I pop the next thing off of it. And if it's not call, I give up. And so at this point, I've either given up or I've matched the pattern. And so now that I've matched the pattern, I want to go backward through the block and look for the last setting of RDI prior to the call. And again, I didn't give anything to trip you up, but there are some weird, I don't think there are any in the Linux system, but there are some weird embedded compilers that do some funny stuff in the startup of the C runtime. Wouldn't matter here. So here we go. We're just going to walk backward through it because that's probably going to be the fastest way to find it. So I set main address to none because that's how if I don't find it, that's how I'm going to signal. And then I go for instruction in reversed block, and reverse block just takes an array and reverses it. Gives me a generator that iterates over a block in reverse. Again, if you didn't know that, that's fine. You didn't need to know it. You could have an index that runs backward. You could pop more things. It doesn't matter. It's not that important. Just how I chose to do it. I print out the instruction I'm looking at with a debug statement. I then get the mnemonic and I check to see if it's a move. If it is a move, hey, that's great. I grab the destination and source operands, right? And those will be there because a move has 2 operands. So destination is the first one, source is the second one. There we go. And what I want is for the destination to be RDI and the source to be an immediate value, an address. And so that's what I look for. I check to see if the source type is immediate, right? And the destination type is a register. So if both those things are true, I'm good. Or if either one of them is false, I got the wrong operand types and I continue around the loop. I check to see if the register name of the destination register, because at this point I know it's a register. I checked it above. I check if that's RDI, and if it's not, then it's the wrong register, and I continue around the loop. So if those things all are satisfied, then my main address is the immediate value, and I'm done. I don't need to add anything to anything or do anything else with it. That's just the value. And since I found it, instead of continuing around the loop or following through, I just break right here, and that's the value of main. So that takes care of move. So up next, I check for LEA. If I find LEA, then I grab the destination and source, just like I did before. And I can do that now because I know that LEA has 2 arguments or 2 operands. I check to see if the source type is right. It's got to be, the destination has to be RDI, like it was before. The source has to be a memory expression, because it's LEA. And the memory expression has to be an RIP relative expression. RIP relative expressions just have the RIP register and the displacement. So all I've got to do is check for that. So I check to see if the source type is a memory and the destination type is a register. And if either one of those is not true, then I've got the wrong thing and I continue around the loop. Then I check to see if the register name for the source is RIP. And if it isn't, I'm in the wrong thing. It's not RIP relative, and I continue around the loop. And then I check to see if the destination register is RDI. And if it's not, I give up, continue around the loop. So if all those conditions are met, then that's easy. I just have to compute 2 things. I have to know what RIP is and what the displacement is, and just add them. So RIP is easy. It's the address of the next instruction in the linear order. So that's the address of the current instruction plus the number of bytes in that instruction. That's the address of the next instruction. That's what goes in RIP. The displacement is just the displacement from the memory expression. I have a little debug statement to tell me what all that stuff is. Main is the sum of those 2. And notice if this is negative, this will return a negative value to me. So I get a negative displacement, which is exactly what I want here. And that works out just like I want it to. And then since I found main, I break. Whew. And now we're done. That's it. So if I found main, if main is none, I didn't find it. And so I write out a message, could not locate it. Otherwise, I print out the address of main. I return 0 because everything worked. And that's it. And then I have this top level boilerplate, which causes it to call main when I run it from the prompt. And that's my little single main method solution. It's a solution. It turns out it's not actually the one I used, and I will post the one I used in addition to this main one if you want to see that too. The one that I actually used when I was checking your homework is one where the different pieces that you saw are broken up into their own functions. So because that's going to be more convenient down the road when I'm trying to write other programs. If I have a solution to finding main, I want that to be in a little function that I can reuse. If I have a solution to extracting a basic block, given a start, I want to pull that out into a function so I can use it, etc. And so I'll post both of them. If you're not running Pilot on your program, you should be. There were several cases where I looked at someone's program, they were having problems, they were struggling, and Pilot would have told them what they were doing wrong. It would have just solved their problem. It would have said, this is bad, you should do this. Or you're probably trying to do this, here's how you should do it. And that would have been great. So run Pilot. I think that's a thing worth doing. Your final program really shouldn't have debugging output. I shouldn't see debugging output in a final submitted program. And there's no reason why I would if you're using the debug statement. Writing a debug statement is exactly as easy as writing a print statement, and that should just be fine. A couple of you should really consider, just put it in the back of your head, maybe think about it from time to time, reading the instructions, because you're giving me a lot of additional output that I don't want. That does not help me. Certainly doesn't help the automated checker to do its work. So I don't need you to give me a discourse on the program. I just need to, your output should match what the example output is. All right. Are there questions about the homework assignment or my solution or any of this? Okay. There's new homework. It's coming up due in 2 days. And I don't think it's all that, I think it's not as challenging as the last one. The last one had a lot of pieces and things going on in it. But if you've done the last one, you probably already have done the piece of extracting a block, given a start. You know how to find basic block leaders. You now know how to look at operands for things. This one should be pretty straightforward, I hope. Get in solutions early and I will check them as usual. I think there's a problem with the date on the assignment. I'll make sure that's correct. So given an unknown ELF, identify and print basic blocks. If you can find main, start from main. If you can't, start from the entry point. And you do the algorithm that we talked about in class. I forget which lecture it's in. Maybe, yeah, I forget. But if you go back and look at them, we actually walk through an example of doing this in class. Identify basic block leaders. So what you'll do is start at the main address and you'll just look at the instruction at that address. And if it's a call or it's a jump or it's a branch, you'll see if the potential targets for that are in scope. And if they are, push them on a stack and keep going until you find the end of the base of what looks to you at the time like the basic block. So then, once you've hit the end of that, you grab the next thing off the stack and you resume the process there, and you just keep going like that. And then in pass 2, just sort the leaders in increasing order, and then for each one, just print the basic block that starts at that location. And remember, here's the only trick to this. This is the trick. I'm telling you what the trick is right now. The trick is a basic block ends when you hit one of those instructions we saw earlier, or in pass 2, when you hit the leader for another basic block, right? Basic blocks don't overlap. A basic block will stop when you hit the next basic block. So you look for the things that end it, like return, and you also look for the things that end it, like the start of the next basic block. All right, keep that in mind. That's the only trick here. Here's a printf statement to write your output. Spacing in this is not significant. The checker will strip off any additional spaces, including between things, and that's fine. Call your program blocks.py and put a blank line between each basic block you print out, and that's it. That's the entirety of the output that you need to emit. Of course, if it's not an ELF file or you can't find the file, you haven't got permission to access it, or you can't decode it as an ELF file, or something else goes wrong, print an error message, right? Handle those cases. But otherwise, I think this is fairly simple. I think. Could be wrong. Never know. Questions about this new homework assignment? Great. When you have questions, and you will, email me. Tools, let's talk about some tools. And the tool for today is the proc file system, and we'll be using that. So let's have a look at it really quickly. If you're not aware of this, there is something called procfs. It was introduced in 1984. So, you know, it's documented in a paper submitted to the Unix conference or summer conference, I believe, and was written into the Unixes of the time and persists in many of them to the present day. And the basic idea is you've got this kernel running and it has all this information. And there are times when your program would like to have that information, but to get it, it has to do a syscall, which takes time, has a context switch, etc. It'd be great if there were a way for the kernel to just directly expose some information for you to go and consume. It makes certain operations a little easier. In fact, the PS command, the process command on Linux gets its information from the proc file system, just because that's the quickest, easiest way to get it. It's documented in section 5 of the man pages, so man5 proc will tell you about it. And there is, of course, kernel.org documentation on it at that link. Now, the problem with the proc file system, and there is a problem with it, is one of the information that's exposed by the proc file system being out of sync with the actual state of the system. And there, you can have race conditions and other things that occur, and it can become more complicated under some of these more modern OSs. Information can be delayed, getting to it, etc. As a result of all this, it was removed a few years back from OpenBSD, and the folks at Apple decided they would just not even bother to implement it in Darwin and Mac OS. And so in those, you need other tools. And there are other tools that do the same kind of thing, right? You can call syscontrol, you can call procmap, a dozen other things that you can call to get the information. It's not all in one convenient, easily accessible place like it is in Linux. So what's in there? What's in the proc file system? Well, there's information for each process. If you just go into that folder, you'll see a whole bunch of directories that are numbers. And those numbers are process IDs. And if you happen to go into one of those, you can look at some stuff. For example, over here, I found the directory for the root process for the Chrome browser. And when I cat command line, which looks like just like a file in there, I see the command line that started it. There it is. I can look at a few files. CWD, exe, and root are symlinks. CWD is the current working directory of the process. So if inside the process you change directory, that'll be reflected here. So you can see the current working directory of the process right here. I wondered, where is my process writing its stuff? I don't see any files. You can go and check that in the proc file system and see where it thinks it's supposed to write its stuff. If it's a chroot process, root will be something else. If it's not, root will be this. And here's the executable. Here's the executable that is been run for that process. There's other information you can get. There's just a ton of stuff. I'm not going to go through all of it because there is really a ton of information in there. So for cat status, and I just grep out the parts that have to do with virtual memory, you'll see that at its peak, Chrome was consuming, you know, not kilobytes, but megabytes of information, and not megabytes, but times 1,000. So there you go. It's consuming a lot of virtual memory. It's a memory hog. Here's the current size of the virtual memory. So a little down from the peak, but still there. A few other little pieces of information down through here. How much is in data, and so on. How much swap being used. All right, there's a directory named self that points to the PID for the process that is currently reading the proc file system. People sometimes get confused because they'll see that and they'll wonder why it's not the PID of their shell. It's because it's probably the PID for ls, because that's actually the process reading it. All right. Another fun thing to do is, since it's world readable, since anyone can get in there and read CPU info, you might like to know if the machine that you're on is subject to a series of attacks. And one way to do that is to look for bugs, and it'll print them out. And it prints it out 4 times because I have 4 cores in this particular machine, and they are all susceptible to meltdown and Spectre and so on. So that's handy if you are a well-meaning person who's just curious. Then you can go find that information there. All right. So with that out of the way, let's talk about a short history of computer memory, of short-term computer memory, of volatile memory. And a history of memory is one of the things that just for some reason delights my sensibilities. So we saw this picture before. This is the basic block diagram of memory and the CPU. They talk to each other over a couple of buses. The address bus is one way. The CPU says, here's an address, which is then received by the memory controller or the memory management system or something else. Something gets this address information. And then data can be sent from memory to the CPU or from the CPU to memory. So on some older systems, this created a certain type of bottleneck. A different type of bottleneck results on more modern systems. But if I'm sending information from memory, then I can't push information out to memory, and vice versa. Depending upon the type of modern system we're talking about, sometimes you have more than one. You have essentially you have basically 2 data buses, and you may have more depending upon how the system is configured. A system like the AVR or the ARM has multiple buses, and they can be different sizes depending upon the particular application you're looking at. All right, so, but the basic notion is CPU's over here, it needs data, it gets it by putting an address on the address bus, and then reading data back from memory or writing data to memory, which looks like an associative array. And on the von Neumann architecture, it's addresses mapping to both data and instructions. And on the Harvard architecture, there's a split. We'll talk about that more in a moment. But that's the basic idea. I've got an associative array of addresses mapping to bytes. Reading from memory is a fetch. So I put an address on the address bus. The memory controller goes I tell it I want to read. The memory controller goes and finds those bytes. It puts those bytes on the data bus, and they come back to me. And now I've got, in this case, 16 bytes. Right? I don't want to waste time sometimes with the lower bits of an address. And in fact, on the x86, I don't waste time with the low 12 bits. Right? I transfer memory back and forth in pages, which are 4,096 bytes in size, because that's just a more efficient way to do it. If you ever want to know how to build a computer memory, in this case, a 16-byte computer memory from scratch and integrate it into your own built from scratch computer, there's a great series of videos where Ben Eater walks you through doing that. And I'm not going to go through those today, but I think they're pretty good. Oops, no, there we go. No, stop. So for the simple process, for very simple processors like the one that from the previous videos, or for the x86 in real mode, there is no memory management, right? So what constitutes memory management? Memory management is your job. It's not the computer's job, it's your job. If you want memory to be allocated, you need to write something that allocates memory. If you want to have a set of memory set aside for some purpose, you need to remember that the memory is set aside for that purpose. And so typically you would build a memory map of your application. You'd go to Walmart, buy a spiral notebook, and fill it with scratching of what goes where, and you'd wind up with a memory map. And if I have blocks of memory, maybe single addresses, sometimes even bits. And some processors have bit addressable memory, so that you can actually address a bit by directly and make changes to it. So you want to keep track of all that. Keeping track of all that results in a memory map, which looks maybe something like what you see over here. This is part of the memory map for the original Pac-Man video game. And you can see up here, we've got some ROM, some RAM, and then we have other information down through here, like whether or not there's a bonus life, etc. So this is a part of the memory map for the original Pac-Man video game. People had to keep track of all this as they were building it. If you wanted something like dynamic allocation, like malloc, then you have to keep track of the top of the heap, you have to increment that when you need to, and make sure it stays below the stack and the stack stays above it. And all those things need to work together. And there's nothing wrong with doing that. In fact, if you go back and look at how malloc is implemented on some older platforms, that's what it does. There's a Harvard architecture. I mentioned it earlier. And in this case, there's separate storage and instruction pathways for data and the program. So you may have more than one data bus because you're accessing different memories. The Arduino, for example, which is powered by the AVR microcontroller, uses a modified Harvard architecture, as does ARM. And there's all sorts of interesting stuff in the AVR architecture in particular. I don't have time to go into it, but it's really kind of a cool little ISR. And so I have Flash, where I would probably store my program. I have EEPROM, where I would store some boot up information and other persistent stuff. And I have data memory that's volatile, that could be in something like DRAM. And registers get mapped into here. The IO registers get mapped into here. There's external IO slot right here. And then I can have the stack down here moving up. And then I have program information here. And so this is my data segment. Over here's my code segment. And over here is my EEPROM segment, my extra segment, we want to call it. And they all can be addressed. And you'll notice the addresses are the same. So the address 40 might be somewhere in here or somewhere in here or somewhere in here, depending upon what I'm trying to do. If you want to know more about Hard versus von Neumann, there's a video here that I will skip, but you're welcome to peruse it. If I can, there we go. The direct access model works well. It's going to work really well if you have discipline, if you plan ahead, right? You go buy your spiral notebook from Walmart and write out what every piece of memory is supposed to do. And if you're only running one process. Now, does it mean you can only run one process with this model? Of course not. Windows, early versions of Windows ran multiple processes using a model like this. Now they use what was called cooperative multitasking. So instead of the processor enforcing a time slice and the OS managing that for you, each process had to at some point turn control explicitly back over to the OS, which would then schedule another process. And if your process never turned control back over, you froze the entire machine, and that was you being a bad citizen. So every process had a token and had to turn that back over. But you can do a lot of neat stuff with this model. In fact, you can do anything with this model, right? It's as Turing complete as any other model. But what if you have, and this was certainly a problem. This was a problem for in particular, if you're old enough to remember the Commodore 64 and the Commodore 128, you might wonder, how does the Commodore 128 work? If it's got 128K of memory and it uses the same processor as the Commodore 64, which has 64K of memory, and it only has 16 address lines, which can only address 64K of memory, how does it have so much more memory? Well, the solution to this tricky conundrum is something called bank switching. Right? The 16-bit address space allows you to address up to 64K, and that's it. But lots of machines had a 16-bit address space, or even smaller. There are some machines with a 12-bit address space that address much larger spaces. And the way they did it was with bank switching. So you pick a special address, usually like an output port that's mapped in the memory somewhere, and you write a value to that output port. And typically the address is hardware mapped, and it latches a value into some register and so on. What you mean by hardware mapped is there is combinatorial logic on the address lines. So when you write to a particular address, it basically turns on its circuit. The circuit then latches the value not into your memory, but into a special register. That register feeds a decoder. We'll talk about that in just a moment. And then that selects one of several different banks of memory. And that memory bank will stay selected until you latch a different value. And in that case, that way, you could have, let's say you have a 16-bit address line and each bank is 64K. You use a single byte that gives you, say you use 8 lines, that can give you up to 256 banks of 64K each. I doubt anyone would do that. That's kind of pathological, but that's the basic idea. In fact, the original Commodore 64 worked this way. It allowed you to swap out ROM for RAM if you didn't need, for example, BASIC. And a decoder looks like this. So here's a 2 to 4 decoder. I have 2 input lines over here. That allows me to specify a binary number from 0 up to 3. 0, 1, 2, and 3. And whichever one I specify enables that particular line of output. So you'll see here, if it's 0, D0 is enabled, everything else is disabled. If it's 1, D1 is enabled, everything else is disabled, etc. And so you can imagine these lines going to the chip select for a particular bank, right? So once I've written 3 in here, this is disabled, this is disabled, this is disabled, and then this is enabled. And bank 3 is the one that's I'm going to be talking to with my usual address lines, etc. And these can get fairly complex. Here is a 4-line decoder. So over here we have 16 lines that could be enabled or disabled. And this is a 4-bit, it's a transparent latch with a 4 to 6 line decoder. And there it is, this little package. And this is part of the data sheet for this particular IC. So 16 bytes of 64K each gives up to a megabyte. And in fact, there were machines built with 16 address lines that addressed a megabyte of memory. I actually worked on some of those. Some of those were telephone switches. So the problem becomes, I'm adding this complexity to it. The problem becomes, how do I control the banks if all the memory gets switched? If all the memory is switched out, then where do I put my control program that's doing the switching, right? Because what happens is memory gets switched out from under me, right? If I'm at address 300 in bank 2 and the instructions cause me to switch to bank 1, suddenly I'm at address 300 and let's say 4 in bank 1. And that better be the right place to be because I have no other control over it. So that can be a bit of trouble. And so often what you might do is have the same code in every bank. So I would set the bank I want, I'd set an address I want, I would jump to the code that does the bank switch for me and then jumps to that address in the new bank. That code would be the same in every bank, so it just works transparently. There are tricks like that that I would use. That's terrible. That's making me do a lot of work. So one solution is to have a secondary microcontroller that just manages the bank switching and the instruction pointer and that stuff for me. What I need is something to manage memory for me. I need another computer, right? I've got my computer over here and it's got memory, but I need a second computer to solve the problem of managing memory for me. And I call that a memory management unit. Now the processor gets to use addresses, and the MMU is responsible for handling how things get mapped into memory. So I've started down a dangerous path, and it's not long before crazy things begin to happen. And one of the crazy things is dynamic address translation. So once you start down this road of bank switching, it's just a short matter of time until you realize everything ought to be bank switched all the time. Right? I should not directly address memory. I shouldn't talk about memory at all. I should let the MMU computer figure that out for me, and I should not have to think about it. And in fact, my addresses should really be sort of virtual addresses, and they'll get resolved to physical addresses by the magical MMU. And so it's not long until you wind up using virtual addresses. In fact, this goes back to 1966. This is a really old development. And it's a really cool development. If you want to read about the origins of it, you can read about it right here. It actually goes back to 65, which is when this was implemented, but I count 66 because January is when they published the paper. And here's a scan of the initial part of that paper. I don't know if you can find it online. You probably can. I did not check before class. I just scanned a copy of mine. So a memory management unit is going to translate virtual addresses, which are things that are used in the CPU, into physical addresses, which are things that are used to talk to things like the DRAM controller. And there are big advantages to this. And I'll list some here. Memory protection, right? Processes get to isolate their memory space from other processes. Okay, if I get the address for something wrong, and I write to that address, I don't corrupt another process. That was something that could happen all the time on DOS and other systems with flat memory. This protects me against that. It also means if I try to jump to a byte of code that's not in my address space, instead of jumping into someone else's address space or going into some bad place, I can segfault, right? I can protect you against a lot of harm and in fact recover and not kill the machine. And that's really helpful. This helps solve the memory fragmentation problem. There are other solutions to it as well, including the buddy system. Memory fragmentation does not go away completely because of this, but it does help solve it because now everything is in these page-sized chunks. And so you get a page and you get a page. And if the pages, even if they're not contiguous, they don't have to be contiguous in physical memory because I can make them look contiguous in virtual memory. Now, some of you may be saying to yourself, well, wait a minute, that moves the problem from physical memory to a fragmentation problem in virtual memory. If you were saying that, you are smart because that's actually what it does. And yes, there is still a memory fragmentation issue with virtual addresses, but I can make the virtual address space so large that it takes a long time for that problem to show up. Okay, and that's what happens in modern machines. And there are other solutions to memory fragmentation as well, like the buddy system. Address translation. The great thing about this is if I write my program to use address 400, you can write your program to use address 400. And since we run in different virtual address spaces on the same, we can run on the same machine. That's great. That's really great. Caching. And caching is enabled because I have this whole other computer, the MMU, which is handling this for me. And now I can implement a level 1 cache right next to my processor, a level 2 cache just adjacent to my processor, a level 3 cache adjacent to all my processors, and that can really cut down on the time I have to spend either getting sole access to the lines, right? If core 1 can go to its local caches and get what it needs, it never has to compete with the other cores or go out and reach out to DRAM, which takes forever. If it can get to level 3 cache, it has to compete with the other cores, and there's an algorithm for this I won't get into. But it still didn't have to go out to DRAM, and that's great. large memories, right? Maybe you've got, 16 gig of memory in your computer. That's great. I've still got a much larger virtual address space. I can make the virtual address space almost as big as I want to make it. And your physical memory pool can be managed by the MMU, and it can look to me like I have this giant address space. And then, of course, I can implement error detection, right? The fact that I have all these other things above it, everything above error detection can help me do error detection for programs, catch problems, and halt your process or give you an error before it takes down the entire machine. The implementation is really simple. Divide memory into pages. Typically, the pages are all the same size, but they don't have to be. And they can, in fact, be different size. There's a couple different sizes you can use on the x86. But typically, the world has kind of settled on 4K pages. That's just where we've landed. We've like 4K should be enough for any page. And that's pretty much where we've landed. We use a page table to keep track of the permissions and the allocation. And we use something called a translation look-aside buffer to keep track of address translation. We'll talk about that more in just a moment. If you want to have it, we're not going to go in depth into the TLB because there's a really good short YouTube video that explains it. And you should watch that if you care about the TLB.
Let's take a look at an example of how the TLB.
Let's not. So you wind up with a memory management unit. And there used to be external memory management unit chips, which allowed you to manage memory. And in fact, here's the one from the Commodore 128. So a view of it. It had a moderately sophisticated memory management unit because, again, it's addressing more memory than it has address lines to address, and it has to manage that in a clever way, and it does. External memory management units used to exist. There's one in this picture. I believe the bottom of this thing is the memory management unit. The System 360 at University of Michigan in '69 had a memory management unit. Not all processors that need it have one built in, so there are sometimes external ones. That's less true today. If you need a memory management unit, you'll just put it on the die with the processor. That is just the normal way to do things. So it's getting harder and harder to find these external memory management units. So this is fun, and hopefully, yeah, it's going to automatically play. Great. So the x86 memory management unit is a fairly complex beast, and it has a lot of different operating modes. And like I said earlier, it's a separate computer. And it is, in fact, a Turing-complete computer. So what you see over on the right-hand side is a computer playing Conway's Game of Life, and it is playing it entirely in the MMU. It's not actually executing any instructions. It's just doing memory faults. That's it. And because you can get away with that, you have it being able to play Game of Life. If you want to see how that works, there's a link there that'll take you to the code in GitHub to do that. I think that's both disturbing that the memory management unit is Turing complete, and also kind of interesting. There are still new architectures out in the world on the rise. HSA is one, something that probably a lot of you have heard of. The idea is I've got a CPU and a GPU, and to talk to the GPU, I have to talk to the CPU. So I want to transfer the buffers, and then I have to queue the job and schedule it. The job starts, it finishes. Now I got to get back to the application and get the buffer and get my results back, stage my results and retrieve them. And this thing here, this weird zigzag, is a problem, right? It requires a lot of stuff happening. It requires stuff being copied. And this thing is the bottleneck, right? The CPU represents a bottleneck between my application and its massive pool of data and the GPU and its massive pool of processors. And what'd be great is if there were just some software here that I used. So I could queue the job and it ran and I got the results back and it was a much cleaner pipeline. And that can be done in a variety of ways. It can be done with new hardware architectures and with some new software architectures. And you can read more about that at the HSA Foundation. So you'll need to understand all this stuff if you're going to write your own operating system. If you're not going to write your own operating system, somebody has solved these problems for you already. Congratulations. You can just use what's there. But you may run into code that deals with memory in Linux, and it's worth knowing how all that stuff fits together. So let's talk about Linux memory management. Linux memory management, it looks like memory management in most operating systems. It looks a lot like Windows, like Mac OS. It looks a lot like the VAX. I mean, it looks like they all look pretty much the same. They've all got sort of the same basic structure to them. That's reassuring and maybe a little disturbing, but that's the way that it is. Each process has a virtual memory map all to itself. So again, address 400 in my memory map can be distinct from address 400 in your memory map. It has runtime data structures like the GOT and the PLT, and those are usually near the bottom of memory, but not actually at the bottom of memory because address 0 would be the null pointer. And it's not wasted memory because, again, virtual memory, which means that physical address 0 in DRAM could be somewhere in my address space, and I wouldn't know because of the virtual memory map. Executable code is typically next in data, and then usually there's a heap that grows toward high memory. There's empty space, and there could be stuff in there. We'll see exactly what's in there a little bit later. That's followed by a stack at high memory that grows toward low memory, and that can be followed by other stuff. There can be stuff above the stack, and in fact, there often is. There's a we'll see what some of that stuff is. So here's a very simplified view of Linux process memory. Unused down here, we have the PLT, the text, the data, the BSS. This is a typical layout of things. And then the heap. Often down here at low memory is where we've included an image of the header for the file that's being run, the ELF headers. Are often mapped to memory down here. So you may see a chunk of memory that looks like data that's actually down here, or like the PLT and the GOT that's down here. Then you have the heap growing up, you have the stack growing down, you have a canary or a trap here in the middle. On Linux, you have other stuff. And then you have some reserved stuff up here at the top. And I've given you a 64-bit address space here. But notice that most of the time, the operating system, unless address space layout randomization is enabled, it's going to start your program here, right? And all these fives, right, as I say, they might indicate that we're in a movie because everything is fives, but really what this is about a third of the address space. So we're about a third of the way along, and that makes sense, right? 5 times 3 is 15. So this is about the 1/3 point of the address space. It's arbitrary, but that's where it is. You can specify other stuff when you link, but if you don't specify, this is typically where you end up. And this makes sense because these are the 48 bits that constitute your available address space. So we have zeros up here at the top. These are 48 bits. So the address space is virtual. It has no obvious relation to physical memory, right? It's just whatever is implemented in the page table. And I want to point out virtual memory addresses don't exist until they're allocated, right? There's nothing there. You may talk about the address, but there might not be anything there. And in fact, it's reasonable to assume that there's probably not. Right? If you use all 48 bits of your address space on the 64-bit x86, you can address up to 2 to the 48th bytes. That's a lot of bytes. It's 281 terabytes. I don't think anyone here has a machine with 281 terabytes of RAM. If you do, I'd be surprised. Maybe you do, I would be shocked. You have to get a motherboard that supports that much RAM. Good luck for that. So let's take a little aside and let's talk about memory hardware. So earlier I mentioned 48 bits. And yes, addresses on the x86 64-bit processor are limited to 48 bits. You don't get to use the full 64 bits for your addresses. You are limited to the lower 48 bits. And on a lot of processors, physical addresses are limited to 40 bits. So 40 bits for physical address space, 48 bits for virtual address space. Virtual address space can be huge. Physical address space can be whatever it is. Newer processors have both of those 48. But, you know, is that really a hardship? 40 bits is still a lot of memory. So we have 40 bits of physical address space, 48 bits of virtual address space, and 64-bit pointers. And in fact, on the machine, I think this comes off the machine I'm on right now. If you look at CPU info in the proc file system and you look for address, you'll find out 40 bits physical, 48 bits virtual. That's your address size. Your page size is 4096. Get that with getconf. So the MMU translates virtual addresses into physical addresses. And physical addresses are almost, but not quite actually physical locations in DRAM. They might be, or they might not be. DRAM has its own controllers. There's another little computer between you and the memory, not just the MMU, but also the DRAM controller and sometimes even logic on the motherboard itself that can do other stuff. Some motherboards allow for randomization of memory on startup. What that means is you can't later on go and pull the sims out of the machine and be able to make sense of it because the memory has been randomized. So it's another security feature. And there are some DRAM controllers that do weird stuff with address translation on their end. So you can't even assume that physical addresses out of the page table are really physically somewhere in DRAM. They are somewhere in DRAM, but not necessarily where you expect. The translation from virtual to physical is done using page tables. If you know what a radix tree is because you had a data structures class once, you're in good shape because that's what these are. They are radix trees. What about that 48-bit, 64-bit thing? Well, the way that works is the top 16 bits are redundant. So these 4 characters right here, each one of these is 4 bits, so that's a total of 16 bits. Those are redundant. They all hold copies of bit 47, which is the last bit here. So in this case, it's a 0, and so these are all 0. Down here, we add 1 to it. Now it's a 1, and so those are all 1. And this is how internally the system reasons about addresses. The actual registers hold whatever they hold, and they can have values up in here. But when you treat them as an address, only the 48 bits here actually matter. So something to keep in mind. Page tables. What's a page table? So we've got a virtual address that's made up of 48 bits. So there's our virtual address, 48 bits, 0 up to 47. And we're going to access it indirectly through 4 levels of page table lookups. Pages are 4K. 4K is 12 bits, right? So 2 to the 10th is 1024. 2 to the 2nd is 4, so that's 4 times 1024 or 4096. So 12 bits, 4096 bytes. So this means the bottom 12 bits, bits 0 through 11, are really just an offset into a particular page. So we can just forget about them because they're just an offset into the page. What we really want to do now is find the page. So the way we do that is through a series of levels. The top bits tell us the level 1 page index. The next few bits tell us the level 2, level 3, and level 4. Now there were 12 here, total of 48. So 48 minus 10 is 38, minus 2 is 36. So I got 36 bits left over here, and I'm dividing them into 4 levels. So there should be 9 bits, 1, 2, 3, 4, 5, 6, 7, 8, 9 in each one of these. So there's 9 bits, 9 bits, 9 bits, and 9 bits. Why 9 bits? Well, remember, a page is 4,096 bytes. A full pointer is 8 bytes. So a single page can hold 4,096 divided by 8. That's right. That's 2 to the 12th divided by 2 to the 3rd, which is 2 to the 9th, which is 512. 512 full 8-byte pointers. So there you go. This tells you which of the 512 pointers you want out of that page. And this tells you which one of the 512 ones you want out of this one, and so on. Well, 512 is not enough different page indices. Well, that's okay, because what I do is chain them. I have 512 here, and these point to something here. And I can have for each one of these another 512 here, so I can have 512 times 512 times 512 times 512 times 4,096. So there we go, right? What is that? That's a 48-bit address space. That's all it is. So now, wait a minute, you might say. You said 8 bytes, 512 8-byte pointers, but that can't be right, because I have to point to a page, and the bottom 12 bits aren't used for that. You just told me they're just an offset into a page, so you don't really need the bottom byte and a half. And the top 16 bits you said aren't used, so you don't need the top 2 bytes. So really, you don't need 8 bytes in here. You need what, 4.5, 5.5, 5.5. So that's not going to work. Why have all that? Well, that's okay, because the extra bits are used by the page table for other information, right? The page table has to encode other stuff like access permissions for these pages. And those are encoded using the 12 bits down here and the 16 bits up here in each of those 8-byte things pointed to at the level 1, level 2, level 3, and level 4 indices. Okay, all right, I suppose. In fact, here's what a page table entry looks like. Remember, a page table entry is going to be 8 bytes long. And so bit position 0 through bit position 63. And here's what each one of those bit positions is doing. Well, where's the address? Well, it's right here. Here's the actual address. So notice the bottom 12 bits that I told you we didn't need, those are right here, right? Present, read write, user supervisor, page level write through. That's important. Maybe we'll talk about that, I think, a little bit later. Cache disable, access, dirty. That's good. We need to know if we need to write this piece of information back to memory if it's dirty in the cache, and so on. And right here, look at this. Physical address of the 4K page referenced by this entry. Ah, this is good. Here's the physical address. How wide is it? It's m-1 bits wide. What? What is m? Well, m is 40 or 48, right? Depending on your processor model. So you might have 40 minus 12, 28 bits, or 40 minus 12 with 36 bits, with the bottom 12 bits all zeros. So the address is aligned on the page boundary. And m can grow, right? I could use this reserve bit here, and I could use these ignored bits here until I grow all the way up from bit 12 up to and including bit 58. So I could have m be fairly large, but I'll never be able to get these last couple because they're used, right? These are used for protection, and these are used for execute controls. This bit's used to execute control. And so there we go. But I have some room for growth in the current architecture. Pages themselves, well, their size can vary. I don't want to get into the details of how this works because it's painful, but I typically have 4K pages. But I could also have 2 meg pages, or I could have 1 gigabyte pages. And you can actually mix those if your OS supports it. Okay, so you can have weird page sizes on the x86. All right, enough of that foolishness. Let's get back to this. Clearly, if you have a gigabyte page, this isn't going to be the right thing. It works a little differently in those cases. If you want to know about that, go and read the Intel Software Development Manual. So once we have an address, right, we have all these bits. These 9 bits tell me an offset into the level 1 page table where I will find an address of another page. And this tells me the offset into that second page where I will find the address of another page. And this tells me the offset into that address where I will find the address of another page. This tells me the offset into that page where I will find the address of an actual page in memory. And this tells me the offset into that page in memory of the byte that I want. And that's how we interpret it. So that all seems like a good just so story. But how do we get started? Where is this level 1 page, right? I know where this one and this one and this one are, but I got to know where this one is to kick off the process. The address of the level 1 page table is held in a register called CR3, Control Register 3. It holds the physical address of the level 1 page table, and you can get its contents with just a simple move, but only from within the kernel. Okay, let's try and see if I have it lying around over here. I do. So here's a little piece of code. It's always fun to try these things. Global main, extern printf. Here's my text section, push, move. And then I take CR3 and I put it in RSI. I put a format string, this format string down here, in RDI. I zero out EAX because I'm about to call printf and I have no floating point arguments to it. And I call printf. Then I zero out EX, leave and return. Pretty simple stuff. I run it. And now let's see what happens when I run my little CR3 program. I get a seg fault. I get a seg fault. In fact, we want to go into the debugger right here. I'm not allowed to access CR3 because I'm not in the kernel. But what about sudo? Everybody look away. There we go. Well, it doesn't matter. Does not matter because elevating to root is not the same as running in the kernel. So I can't do that. I have to run some code equivalent to this in the kernel, and I couldn't use printf because that's not, if you've ever written kernel code, it's a whole other thing. It's a whole other world. So, all right, only within the kernel. It calls a processor exception, which Linux interprets every processor exception as a seg fault, basically. Additionally, I have to align this register on a page boundary, so all this stuff has to be 0. So that's how it gets kicked off. And so here's how it works. Here's how you find stuff actually in physical memory. So here we have a big pool of physical memory. Here we have an address that's 48 bits long. CR3 points to a 4K page table. Addresses are increasing in this direction. The first 9 bytes give us an offset into that table that points to a new page, which we go get. And the second one points to an offset in there, and the same thing for the third one, and the same thing for the fourth one. And then this guy right here, this 8-byte slot right here is an address of a 4K page in physical memory. And the last 12 bits Well, they point you to a particular byte inside that page. Right? 9 bytes would pick out one of the 512 8-byte regions, but 12 bytes will get you all the way down, adds the 3 to pick out one of the 8 bytes. And there you go. And that's how you get all the way down. Now, if this seems like a process that would take a while, right? Because where are these page tables located? They're in physical memory. They are in memory. So if you give me an address, I have to perform 1, 2, 3, 4, 5, maybe 6 fetches to get here. That's terrible. I can't do that every time I have to deal with an address. Okay. So, and in fact, I don't. What I do to speed things up is I introduce a translation look-aside buffer. And basically what it does is it's a array. And I look for this initial stuff in the array. And if I find it, I have the immediate map to the physical address, and I'm good. And every time I access one of these, I can add something in here. So I know where a page is located. There's a little more to the x86 TLB than just that, but again, go read the developer manual. All right, so that was a lot about how memory actually works. Long aside, let's take a 5-minute break. And when we come back, we will resume chatting about memory. So if you'd like to see how addresses are used in your program, and you already know this part, you can use GDB, for instance, to do that. So up here, I started GDB with ls, and I do info file, and it will tell me about the entry point, and it will tell me about the chunks of memory that would be allocated for ls. And not every single byte is always going to be used. And I like picking on ls because here we have position 318, not 0, through 334. And then there's a gap and 338 through 358, right? And because of alignment. And you'll see that if you look down the column here, 888, here's one that's a little bit odd, C, 000, here's the 6, 888, 00000. You're gonna see lots of things that are nicely aligned. And over here it'll be much more messy, right? There's a 5. 5 is not aligned on anything. That's terrible. B, what the heck is that? Right, so there you go. Now these are addresses as they appear in the file before it's loaded into memory. So if I used readelf and I asked readelf, what's the entry point? I get 6810 hex as my answer. When I'm running, it's not the same. And so how can I see the addresses of the running program? Well, what I can do is I can go ahead and do start I in GDB. And then I'll get this message using the running image of child process, right? Before, it didn't give me that. Before it said, here's a file. This is its file type. Here's the information I got from the file. Now it says there's a native process that's actually running. What you see is going to come from the image of this process. 55822 is the PID. And the entry point is now this, and there are all those 5s, which indicates either that we're in a movie or we're at 1/3 of the 48-bit address space. And here are the allocations. Okay, and they're going to be offset by some amount, and that amount might be this number, or 555555554 It might be 1 offset. Or it might be something that is chosen by the address space layout randomization algorithm if it's enabled. You can enable it within GDB, and you'll see all that here. So these are only the addresses at runtime because we got relocated, which is perfectly normal. In this case, the addresses are final. Up here, they're just sort of tentative offsets, And then down here, their final addresses. And that can be helpful, right? If you're inspecting a running process, you'd like to know that. Can you take a look at the running process? Turns out you can. So within GDB, you can say info proc, and that'll tell you the process ID. In fact, if you go back one, info file will also tell you the process ID, but it'll give you a lot of other information. And you may scroll off the screen. Info proc is a little bit easier. Give you the command line, the current working directory, and the link to the executable. Where does it get this stuff? It gets it out of the proc file system. There you go. So we might as well look in the proc file system to see what's there. So if we go and look in proc and we put in the process ID and we say mem after this, we can begin to take a look at what's in memory. And this is not, how did this make this into the slide? I must have been so tired when I made this. Mem is not right. It should be maps. So just in your brain, edit this to be maps. Sorry about that. I'll fix the slides. Maps. I'm clearly too tired to be making slides. So what we start seeing is the memory mapping for the particular process. And so here's that base start address up through here. And if we look back here, we'll see we have stuff in that space, but not necessarily consuming the entire space. So the start address is here in hex. Here's the end address, also in hex. If we gray out the top 5s, you can sort of see how big each one of these is, right? This is about 2,000 hex, or about 2 pages. 1,000 hex is I think a page. My brain is not working this morning. This is bigger, quite a bit bigger actually. This is modestly sized. This is fairly smallish, etc. And then down here at the bottom, we have a heap. So addresses are shown here as 6 bytes, right? There's each 2 characters is 1 byte, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, or 6 bytes, or 48 bits. So we're seeing a 48-bit address. Permissions associated with each chunk are given. So this first chunk has read permissions. We'll talk about P in a bit. Read. This next one is read and execute. That should give you a hint as to what's in it. This next one is just read, and this is read write. So what's in here? Well, the PLT and the GOT. What's in here? Text, data, BSS. Right? You can sort of read these out without too much trouble and know what they are, because you know how that stuff works. Here is a file offset if it's relevant. A file offset, if that's right. So, and this is also in hex. So at an offset of 4,000 hex into this file, we would find the contents that go in here. Some of these are zeros. That just means that it could be the offset is 0, like up here, or it could be that it's not meaningful, like down here. Here we have major and minor device numbers if this comes from a file. So I don't know how many of you know what major and minor device numbers are in Unixes. Basically, the major device number identifies a device driver in the kernel, and they're identified by number. The second, the minor device number, is provided to the driver for the major device and identifies something with it that makes sense with respect to that device. So for example, in this case, we have 103. And since we're talking about a file in the file system, you'd be reasonably safe in concluding that this is something to do with a disk, and that maybe this was something to do with a partition. We can in fact go and take a look, right? I don't want you to be guessing. We can actually find out. So it turns out these are hexadecimal, which is a dirty trick. You might look at this and think, I can't find device 103. You can't find device 103 because it's hexadecimal. So let's convert it to decimal. This is the little bash trick that will do it. And it turns out it's device 259. So then I go into /dev and I grep for 259 and I get this. So what is this? NVMe 0. That is the first NVMe drive in my laptop where I made this slide. And you'll see it's got 4 partitions, and LS lives in partition 2. There's the major and minor device numbers. I get to see those when I do LS in dev. I don't see the size of things, I see the device numbers. So there it is. So now I know which partition of which device this lives on. The next thing is the file number. What is that? That's an inode. So major, minor, inode, if relevant, and then offset. So you get right down to the bytes. Now, how do I convert this into something meaningful? Well, you can see inode numbers with ls-i. I don't know if you ever have tried that, but there they are. They're the inode numbers for the various files that are in this particular folder. And you can do this way as well and see the inode numbers over here on the side. So I could do that, or I can do find, and there is in fact a way to look for inodes in here. That's one. There's a simpler one that I'm not finding quickly on the man page, so I'll just go back here and say look for it with -inum. And so find will let you find it. There's not an easy, quick, direct way to do it. The fastest way I know of to find a file by inode number is to use this trick, which is to use debugfs, and you've got to be root to do it. So debugfs, I want to reverse, and here's what I want, and I'm going to look for it on this particular device. And when I do this, and I give it this number, it tells me it's user bin ls. So a lot of work for me to figure out that this thing over here is correct. But I did the work, right? I figured out it was this based on the device numbers. I figured out it was this file based on the inode. There you go. You might as well understand what all the columns in these outputs are. At the end there, it's done the work for you and converted that to the path, or to, in this case, keep the content. And you can figure out this stuff. Like earlier, I was sort of walking through it saying PLT, text, so on. You can figure out what these things are by looking at the permissions or maybe at other hints. This is likely where your data, your pre-initialized read-only data is. This is likely where BSS is because it's writable and not executable. So that would make sense. And if you don't have all those other hints, like someone has scrubbed the header of their file and something is in memory and you don't know much about it, you can use this kind of information to help you get insight into what's happening. And then here's the heap. So the heap isn't backed by a file, and so I don't have any device numbers or inodes or offsets. It's readable and writable, but not executable. I don't want an executable heap unless I really, really, really have to have it. I don't. And you'll notice this address right here is the highest address for my program. It represents the end of the heap. And it's got a special name. This is called the program break. It is the lowest address outside the program space, right? Each of these ranges, right? We see 8,000 here and 8,000 here. It's not in both chunks, right? This is in the chunk, so this is inclusive, and this is exclusive. This is the first address outside the chunk, and the first address in this chunk, etc. And so this is the first address beyond the end of my program, or you can just think of it as the end of the program. It's a program break. So it marks the end of the heap, typically. The program break is managed by, no shock here, the operating system. And there is a system call to move it, called the break system call, which is system call 12, and you give it a new address in RDI, and that moves the break. If you use break with RDI equals 0 on Linux, it will give you back the current state of the program break. And there are one or two other ways to get it as well, including just looking at the map. All right. We'll talk about break a little more later on. In fact, I should take that back. We'll talk about break right now, apparently. My slides have surprised me. So the program break gets manipulated, like I said, by this system call. You give it a new address in here, or you give it a 0. Nothing too sophisticated here, right? I put 12 in REX, I put 0 or my new address in RDI, and I do a syscall, and that's it. What does that do? Let's go see. So we'll come back over here. And I believe I have a break.asm, and I do. And I don't want to go too in depth into all of this. This is from a prior class, so it's got some things for you to try out and questions in here to ask and so on. But it's maybe an example of how you would write a larger assembly program. So I've got global start, so you can assume I'm not starting with the C runtime. I've got default rel, so you can assume I'm making a position independent executable. And if you wanted to confirm that suspicion, you could look right up here and see that I've got -pi. I define this thing to indicate that functions that follow the calling conventions. Not every function has to. If I know enough about a leaf function, then maybe I won't follow the calling convention. I'll know that, I restore all the registers I use, in which case I don't care about any of that. Sys exit group is what I'll use here instead of just exit. That's 231. Break, as we talked about, is 12. Write is 1. Those are the system calls I'll use. Standard out isn't 1. A page is 4096 bytes. The length of a hexadecimal number is 16, and OK or no OK is 0. Hooray. Here's my text section. I'm going to get the program break and print it. So how do I do that? Well, I put 12 in EAX. I 0 out EDI, and I do a syscall. And because EDI is 0, it gives me back the current program break in RAX. In fact, it always does that. Even when I move it, it'll give me back the current program break in RAX. I put RAX and RDI, and I call print hex and print new line, little routines that we could look at there later on in here. And then I do something. In this case, I put sysbreak back in EAX. I put the address of RSP, but the contents of RSP in RDI. What is that? I put page in RDI. I add the page links to RDI, and I do a syscall. So what happened here with this thing? Well, if we look right up here, I sort of glossed over it. After the system call, I pushed RAX because I'm going to have to use it again later. So I saved the previous break value, and then I pull it out down here and I add a page to it. So I'm basically saying, I want the new page break to be 1 page more than it was. So I'm going to increase it by 4096 bytes. I do a syscall, and then I take RAX, put it in RDI, print it out. Now, why did I do this move and not a pop? I did this because I want to leave it on the stack a little bit longer and then use it down here. So here I actually pop it. And then I say I want 32,768 more pages. I want a lot more memory. And I add that to the previous program break, and I do a syscall, and then I print that out. And then I exit the program. And if I kept going, I'd run into the various subroutines that I mentioned earlier, but we're not going to worry about that. So I should get 3 results. I should get the program break at the start, the program break with an additional page allocated, and then a program break with 32,768 additional pages allocated. So let's make it. And let's run it. And here's my results. So here is my initial program break. Here, I've added a page to it, and you can see since 4096 is 1000 hex, I've just increased that by 1. And then here I've added a lot of extra memory to it, right? A lot of extra memory to the program break. There we go. There's PTS2. Nope. What I did not do is say break. There we go. Okay, so we can also run through this real quickly inside the debugger, just to be sure we understand all of this. And I've got the output directed to this little thing down here. So the output will come out in this little table. There's a little warning about it, but you can ignore that. And so here we go. We've put 12 EAX right here. We then zero out EDI, and we do the syscall to get the program break, and there it is. But is this right? Well, here's the process. And here's the memory map for that process. So you see, I've started break, and here are the different pieces of it. Here's some slack space. There's some other stuff we'll talk about later, but you'll notice something missing. There's no heap, right? Nothing in here is labeled heap. And where does the program end? It ends right here at 8,000. So what did I get back when I did the syscall? I got back with an RAX. I got back 8,000, which if I keep going, I'll print it, and then I'll print a new line. There we go. And so there's the current program break, which is in fact the end of the program itself. So let's watch this as we go through this. And so every 2 seconds, it'll update that. And we'll see if anything changes as we walk through the program and try to manipulate the program break. So again, we load 12 into EAX. We go ahead and load the old program break into RDI. We add a page to it. And so now we see it says it has 9,000 here. Program break hadn't changed. We do the syscall, and something happens over here. Notice this is still 8,000, but now we have a new slot, 8,000 to 9,000, and it is labeled heap. So now we actually have a little bit of heap. In fact, we have 1 page of heap. So let's keep going. We're going to print out the new program break, which is 9,000. We can load this in. We add all those pages to it. And we're going to do a syscall. And so what do you think is going to happen? What should happen, I think, is this, the address of the end of the heap should be changed. So let's take one more step. Do the syscall. And sure enough, that's what happened, right? So now it is a little hard to see, right? 55, 8,000, 55, 8,000, but there's a D right there. We've added a lot of memory to our heap. We can print out the new one and do our thread exit, and we're done. And of course, the process terminates, so we have no more map over here. All right. So that's pretty much how you use break. Pretty simple stuff. So back to the memory map. So we're running out of time too, so I'll try to go super fast. Some other things are in here: VVAR and VDSO. What are those? VDSO is the virtual dynamic shared object. So SO usually a shared object. Virtual dynamic, what is that? This is where the kernel exposes some routines for you to use, and VVAR is where it exposes some data associated with those routines. And you'll notice that both of them are read-only, and VDSO is executable. There are cases where I would like to get information like the time of day and I'd like to do it without having to pay all the overhead of doing a context switch for a system call into the kernel. And this gives me a way to do that. This is a mechanism for me to use certain system calls very fast. They run in user space. The data they need is in user space as well. And there you have it. And how does that work? Just memory mapping, right? The data is staged by the kernel in a particular spot in memory, which is then also mapped into the process space so that you can see it. Same thing for this. All right. What's here? Oh, look at this. It's our old friend, the dynamic linker / dynamic loader / program loader, whatever you want to call it. Here it is. And it looks just like our program up here, right? It's got its own little sections. This one's executable, read only, read and write. So this is probably its data and its BSS, and that's probably its linkage tables. So there you go. So it has to be in memory too, because it has to run at the same time our program is running. And that's where it lives. And it typically lives at 2/3 of the address space. So we expect to double this, and it's more or less in that range. And it's of course bumping up against the memory limit, right? Because 48 bits. And so if that becomes an 8, we've flipped over to the one where it copies everything. Here we have the stack. Our old friend, the stack. It's readable and writable and not executable. We don't want an executable stack. Boo, executable stack. And look at this. The stack is not very large. It turns out this is about 132K. The stack can grow. It can grow up to 8 megabytes in size, unless you modify the operating system's limit, and they can grow larger at that point. But there's our friend, the stack. And you can specify how the stack gets set up when you're building your file. When you're actually building your ELF file, you can actually set up information about the stack segment in your file. You've seen that. And then up here at very high memory, you see we've tripped over into the place where all the bits get copied. We have this thing, vsyscall. What is vsyscall? This is an older version of this. vsyscall is a space for fast system calls. It's not readable or writable. It's kind of weird, but it is executable. And so you can do it provides a fast system call interface, the older version of the fast system call interfaces. Other processes vary. This is the memory map of Python 3.9 while it's running. It's got a heap. It's got, if you see libtinfo, libthreadline, you're wondering how you get access to libc at runtime. They get mapped into memory just like everything else. So these get mapped in, these get mapped in. Information about your locale, the strings for your locale gets mapped in. Python needs that. And so if I wanted to call printf, it's somewhere down in here. All right, it's in one of these sections, probably right here because it's got to be callable, so it's in the executable section. And then there's plenty more. Here's the compression library. Here is the dynamic loader, and then the usual stuff: stack, vvar, vdso, and vsyscall. In this case, it put them down here. It puts them wherever it needs to put them as it's staging things. All right. Another way in which memory gets allocated on Linux is through something called mmap. Mmap is another system call. In this case, it's rex = 9, and it is way more complicated than break. So in particular, I set rex to 9, and then I have to fill out all the other 6 registers. So the first one, I put the preferred address that I want to allocate, or I put 0. This is a hint to the operating system. It tries to allocate memory close to this address. And this address might be in use, in which case it can't allocate memory there. So it tries to allocate close to that. Or if I provide it with a 0, I just say, give me memory anywhere you want to give it to me. I don't care where it is. The length, how much memory do I want, right? This is where I would put 4096 for a page or some bigger number for more. What protection modes do I want? So you may have wondered, I was moving break around, but I wasn't saying I want readable only memory or I want executable memory. Here's where I can specify that. I set this up with the protection modes I want, like read only or executable. Here are some flags. What are the flags? Well, they're things like whether the memory is private or shared, and whether or not it's backed by a file. Right? We saw that some things were backed by files. How does that happen? Well, it happens by me specifying the correct flag and then giving you a file descriptor and an offset into the file. And so when I do all of that, then you can actually map a file into memory. Now, the changes to the file get written back to the file. Depends on the flags. Okay, there we go. Let's look at a quick example. I'm not going to go through too in depth into this. So down here, we grab a single page, and you'll notice that we set RDI to 0. So we're going to say, I want a page of memory, but you, the operating system, get to choose where that is. How much space do I want? A page. So I give it my size of 4096. I go ahead and mark it as readable and writable. Where did these constants come from? They came from right up here. Where did I get them? I got them out of user include mman common.h. So I give them those constants. I want it to be anonymous. What does anonymous mean? That just means it's not backed by a file. It's just anonymous memory. It's not backed by a file in the file system. And private. I don't have time to go into shared and private. So if you want to know, email me or just read documentation. That would do it too. Man mmap will give you that. I don't have a file descriptor, so I set that to -1 because that's what the specification says you need to do. There's no file offset, so I just set that to 0. So all my registers have now been set, and I do a syscall, and this should give me some memory. Then I take the address it gave me, and I store it on the stack. And I put it in this place I reserved. In fact, I reserved space right here for it. And I should mention this real quickly. If you're going to reserve space on the stack like this, you should do it first before you push a lot of other stuff, because the math is just easier, right? If I reserve the space here, I know it's RBP plus 8. If I push 5 or 6 things, then I've got to do math. I have to figure out 5 or 6 times 8 and then add that to the already 8. And then I don't want to do that. So my suggestion to you is reserve stack early if you want to reserve stack. All right, I take REX, which is still the return. I move it into RDI and I print it out, same as before. Now I'm going to go get a large chunk. How big a chunk? Same as before, 32,000 pages. This time I want it to be read only. So I say read, write, and execute. So does that sound great? Readable, writable, and executable memory. I love that. That's my favorite kind of memory, the kind I really want, because I can get into all kinds of mischief with that sort of memory. That's great. I mark it as anonymous and private. I set my file information. I do a syscall, and I save this in the next memory slot, which is RBP 16. I move it into RDI and I print it out. And then I do it wrong. So down here, I set up to call it page read write. I say anonymous, but I don't say anything about whether it's private or shared. This is going to be a problem. I then do this so you can see how problems get reported. And then I begin deallocating chunks, and I deallocate first half of the big chunk. I don't deallocate the entire big chunk. I just deallocate half of it. I deallocate the page, and I deallocate the other half of the big chunk, and I'm done. So, oops. I don't know if I built it or not. I have apparently built it. Okay, no, I have not. Now I have. There we go. So, real quickly, let's walk through this and see what happens. Once I run it, boom, now I actually have a memory map I can go look at. Info proc would do it, or I could come over here, I guess, and do PS XF, and I could look for GDB, And then I can see that here's the process running, and it's 180.910, which is what I got over here too, which is good. And I can watch cat proc 180.910 maps. And there we go. That's the memory map for my little simple process. And again, notice no heap. And so let's go ahead and go through it. So I start loading stuff into registers. This is my -1. That's my 64-bit 2's complement -1. And I'm ready to do the system call. And let's see where it's going to go. I don't know. I would guess, is there a convenient gap? We need to B, C. Look at that. So watch this area right here. This is a 1-page gap. Let's see where it puts it. Oh, look at there. I was right. It put in that 1-page gap. Mmap, for some reason, loves to do this. It loves to find the tiniest little spot and put it in there because, again, it's trying to reduce memory fragmentation. And so it puts it in here. And there's my readable, writable 1 page of memory. So that's great. Let's keep going. We're going to print out the address, and we see it's at FFB1000. And sure enough, it's at FFB1000. And you notice I still don't have a heap. No heap up here. I just got a chunk of memory given to me way up here by the system. So I'll keep going. I'll load in the big chunk, and I'm about to do a syscall. And then I do the syscall, and it shows up right here. So there it is. And notice it's still no heap. This is just a chunk of memory I get to play with. And look at that. That's my favorite kind of memory. It's readable, writable, and executable. Here's where all my self-modifying code is going to go. I'm going to have a good time with that. So we keep going. I load in some bad stuff, and I do a syscall. And I don't get an exception, no processor exception. But what I do get is, instead of getting back RAX equal to a nice address, I get back RAX equal to -22. What is -22? That is, in fact, an errno value. And I can look that up in the errno.h. I think it's in errno basic.h, which is in basic ASM. I'm saying all this when I should just be looking it up for you. ASM generic, that's what I'm trying to say. There we go. And I believe there's an errno base. There it is. And eno int is what I think it is, which would be 22. And look at that. Invalid argument. So I got back an invalid argument. Did not like what I was giving it. All right. So let's keep going. We print it out. And now we're in the process of deallocation. So we're going to deallocate the first half of this piece right here. So let's watch this and see how this changes. And oops, you saw that, right? This over here changed. It deallocated the first half of it. That's fine. We still have the other half left. So now we're going to deallocate the single page, and that was down here. It was the one that was in between these other ones. So we do a syscall, and that page goes away. And now we're going to deallocate the rest of this chunk here. And we do. And that's it. And then we're done. So that is really quickly how mmap works. Well, that's all well and good. And in fact, there are programs that will do that kind of thing. And your C code can do that. If you want to have a readable, writable, executable chunk of memory, and who wouldn't, you're going to want to do that. And it's very doable. So, but for the most part, you can use the C standard library. And the routines that you'll be using, right, standard lib.h gives you access to what's in libc.so, and that's malloc, calloc, realloc, and free. Those are the ones, right? malloc gives you a slab of memory. Calloc gives you a zeroed out slab of memory. Realloc modifies an allocation. Free frees an allocation. And use them like you'd use any other function. So here's a snippet of some assembly code. I declare those as external. I have to link with the C library. And then I would basically put how much I want in EDI, and I'd call malloc. And that would allocate that for me because malloc only has one argument. First argument goes in EDI, that's easy. I want to free it later. In this case, the pointer comes back to me in RAX. So in this case, to deallocate, I take that pointer that came back to me, stick it in RDI, and call free. And there you go. Super, super easy. If that's all you want to do, you're good. It's easy to do that. Malloc and free, I do in fact have an example and barely enough time to try to show you how that works. There we go. Really quickly, it looks very much the same as the other ones. All these, by the way, are up on iLearn for today's class. Same basic stuff. I'm gonna allocate some space, get the program break and print it. I allocate a page. I allocate a bunch of pages. I then free the space and I'm done. So let's do that. Gotta run it. And I'm at this process. So let's go watch the memory map for that process. There it is. Can make it a little wider. There we go. And let's just walk through it. So aligning, doing a few other things. We're at start. I want to be at main. So let's go ahead and be at main. There we go. Now we're happy. So reserve some space on the stack, do a few other things. And now we're ready to do our first syscall. Syscall 12, which is break, and 0, which means give me the current break. So we do that and we print it out. Here's the current program break, 59,000. Now, if you were paying attention, this was the program break, 59,000, but you will notice it's no longer the program break. The program break is now 8,000. What the heck happened, right? This isn't right anymore. The moment I printed it out, it became wrong. I suddenly had a heap. Why is that? It's because glibc needs space too, and it's going to allocate it in the heap. It's going to move the program break in order to get its space, and it did. So it used malloc. Malloc had to allocate some space, and that space was in the heap. So now the program break is actually here, and we have a heap. So some memory stuff happened just because I wanted to print out a value. This is why you write your own print stuff. So now I'm going to malloc a page. So what do you think is going to happen? I think this is going to increase by 1. So instead of 57A,000, it would be 57B,000. Let's try it and see. Allocated that page. Got back the address of that page, and nothing here changed. And in fact, the page address I got back, 96B0, is inside this space. What's happening here is when you use malloc or its friends, they set up a series of tables in this space, allocate a big chunk of it, and then they manage this pool of memory right here, and they grow it if they have to, but otherwise they just manage that pool. Okay, well, I want to force this to get bigger. So let me go ahead and allocate a big chunk of memory. So I'll play the game of printing out the break again, which hadn't changed. And now I'm going to allocate a big chunk of memory. What do you think is going to happen? Think this is going to grow by some big chunk? Let's see. Let's do it. And it did not. It stayed exactly the same, but suddenly we have this. We have another chunk of memory. So instead of malloc just growing the break, moving the break, it went ahead and called mmap and grabbed a bunch of other memory. And that's interesting. So back over here, we look at the program break again, we do some other things and print it out. There it is. And the program break has not changed, even though the program has all this other memory. So we'll keep going. We're going to free a chunk of memory. And you see that big chunk went away. We freed it. And now we're going to free that smaller chunk, the page that was in here. So we free it. And when we do, nothing changes, because what all that happened was the tables in here got modified to indicate that that page was free. And we're done. So that's it. So malloc, story behind malloc is it will go ahead and it'll move the break, or it'll mmap, depending typically on the size of the memory you want to allocate, or other features like the distance from the Earth to the moon, or the phase of the moon, or how it feels. It just does whatever it wants to do. And it depends upon the particular version of the malloc algorithm you have as to how that operates. But now you know how malloc works, right? It's either moving the break and maintaining its tables, or it's mmapping and maintaining its tables. You know how break works, you know how mmap works. That's your whirlwind tour of Linux memory. Next time, we will go back out of this world of the details of Linux and get into more type theory with the Mycroft paper.